Okay, sorting. How much did we talk about sorting last semester? I can't really remember. It wasn't a lot, I know that.
We looked at like 5 algorithms.
We talked about a couple of them. Yeah. Okay, well, we're going to revisit several of the ones that we would have briefly talked about last semester, but we're going to actually talk about them in detail now that we're better equipped with the tools to do so. So, sorting. Sorting, like searching, is a very classic problem. I mean, it's a problem we're all familiar with. I know you've all sorted things before. Just like I knew you all searched for something before. I know you've all sorted things before. And because of it, you have executed some algorithm, but you probably didn't spend a lot of time thinking about the algorithm you were using. You just sorted things. But at the end of the day, you still used an algorithm whether you like it or not. You may not be able to identify what you've done, or maybe you can. Maybe after we talk about a couple sorting algorithms, you'll be like, oh yeah, that's basically what I do. What's interesting about sorting, in addition to being well-defined, it's well understood, you all know what the problem is, you know what their solution should be. In addition to that, like it might seem like sorting is trivial. Like sorting, we all do it. But until relatively recently, I shouldn't say we've been bad at it. That's really not the right way to say it. But until relatively recently, no one had defined a good sorting algorithm. Since the beginning of time, humans have been sorting things, and it's unlikely they followed any of the good algorithms. And when I say good algorithm, I mean in terms of computational complexity. A lot of the algorithms we're going to talk about in this first set are all going to be the intuitive ones that you've probably all more or less, like you can wrap your head around in terms of the idea, maybe you've used them before to sort things, whether you like it or not. It's the next topic where we cover the more sophisticated ones. But those sophisticated ones are relatively newly formalized, and chances are people never really did them before. And it's kind of amusing because you think it's such a trivial problem. Yeah, great. Except not in the last century, we only just got good at it. So maybe it's not as trivial as you think. But because it's well understood, it's easy to use as a, I don't want to say toy problem because that kind of like trivializes the problem, but it's a good quintessential problem to look at because it gives us some insights into how cleverness and ideas can be used to improve your algorithm. Just as a heads up, there's going to be several images that you'll see. They're all taken from Wikipedia. If you click the image, it'll just link you right to the article. So, sorting problem. Given a collection of things, I don't care if they're numbers, strings, people, car parts, whatever. The goal is to arrange that collection of things such that they are in some order that we want. The order we want depends on what we're doing. So if I say sort these numbers in ascending order, okay, you know what that means, right? Really, if I say sort these things without being more specific, what does that mean? Though with things like natural numbers, if I say sort these numbers, the natural thing you would think of is, well, ascending order. But if I gave you a list of names and I said sort these things, you'll probably think alphabetically, but maybe it wasn't. If I give you a list of car parts and I say sort them, you're going to ask me, how? What's the order? So the order what in order means, however, will depend on what is being sorted. Like I just said, numbers come with an intrinsic ordering, natural numbers, whatever. And they use a natural order. This order is referred to as the class's natural ordering, and the class's compare to method is referred to as its natural comparison method. Basically, if you look at natural numbers, and you know what their ordering is, and you go look at the compare to, yeah, it's the same. Right? Because there is a natural ordering for these things. Strings could be alphabetical or maybe by length. People by height or maybe age or month and day of birthday, I don't know. But the point is how we want to order them could differ depending on the situation. Car parts by their mass, maybe part number, production date, volume, the amount of dust particles on the surface, I don't care. It could be anything we want. Now with numbers, there's no need to ask. You know what it is. right? You know what I say. Unless I go out of my way to say sort these things in descending order, you're going to assume it means ascending order. The orderness, okay, but with other things, a well-defined ordering is needed for the things, and it's the things themselves that define the ordering. The sorting algorithms, for example, they don't define the ordering, they use a defined ordering for the sorting purposes. The elements themselves define the ordering, like the natural numbers have an ordering. Any method every class you make that has a compare to, it's comparable, you've defined that ordering. It's for the objects themselves that have the ordering. The algorithms themselves just use the ordering that the objects have for sorting purposes. But they don't, the sorting algorithms don't define the ordering. More complex orderings can be defined, like you're currently doing in assignment 4 with that comparator thing, right? It's a little bit more complex than just less than or equal to. There's a lot of rules and whatever. Okay, for ease, for this particular topic, this is just a note here, numbers are used in the examples, but the idea is just generalizable to anything that has an ordering defined for them, so just to be very clear. So here a collection of numbers is considered ordered if and only if the elements are monotonically increasing. And this is just a fancy way of saying the numbers are always increasing or equal, but are never decreasing. That's just a fancy way of saying they're ordered. Okay? If you have equal numbers, yeah, they're right next to each other, and the order that those equal numbers come in doesn't really matter. But it's monotonically increasing. So 1, 2, 3, 5, 5, 6, 8, 8, 8, 9, that's a monotonically increasing series. They're just sorted, okay? BOGO sort. Here's a fun idea. Given a function called isSorted, it takes a collection. I'm saying you've got this function that exists, and here's what that function does. It'll look at that collection and tell you if the elements in that collection is sorted or not. That's all it's doing. And the computational complexity of this is going to be linear because it has to look at all the elements in order to conclude if they're in order or not. Because everything could be in order until you look at that last element, right? And maybe that last element isn't in order, then you conclude it's not in order. But in order to conclude that it is in order, you have to look at everything, right? So it's linear. So given another function called shuffle collection, that randomly shuffles the collection arbitrarily, it just shuffles them. Like imagine I gave you a deck of cards and said shuffle. The deck of cards is your collection. The computational complexity of shuffling, depending on the algorithm you use, it'll be linear. Okay? That's what it'll be. So we could define a sorting algorithm like this. While not is sorted, shuffle. Basically, what that means is I give you a deck of 52 cards and I tell you to shuffle it. And then you need to go check, is it sorted? If it is, you're done. If it's not, you shuffle it again. And then you check if it's sorted. If it is, you're done. If not, well, you keep going. So shuffling is linear. Checking if the data is sorted is linear. But what's the computational complexity of this algorithm there? While not is sorted, shuffle. What's the computational complexity of the sorting algorithm? Why?
Because one shuffle, I'm assuming, is like, what's it called? Just a unit of time, and then you have to look over each thing to see if it's sorted.
Yeah, but how many times do I have to shuffle it in order to get a sorted collection?
As long as it's not in order.
As long as it's not in order. So we got a bit of a problem. Because how do we bound that? I mean, it's possible that I sit here and shuffle the deck of 52 cards to get the exact same permutation every time. That's possible. Exceptionally unlikely. But it's possible. So this particular thing, best case scenario, we get lucky with the collection already being sorted. So I immediately check, is it sorted? It is. I'm done. Oh, whatever. It's linear time to check if it's sorted. But if it's not sorted and I need to shuffle it, I'm going to have to keep doing this. And, I mean, like, if I'm shuffling 52 Can someone do a quick lookup of how many permutations of 52 cards there are? Wait, I think I've got it right there, actually. I do, so no need to tell me. What does it say? It's possible to get really unlucky and shuffle the elements such that they're the same, not in order thing. That's possible. Unlikely, but it's possible. But you gotta figure, every time I shuffle those cards, like, depending on how good my shuffle is, they're independent things. All right? So, if I have permutation A, and permutation B is the sorted permutation, the likelihood of me shuffling permutation A and getting permutation A again is the same likelihood as getting permutation B. Right? So I'm just as likely to get it right as wrong. So this is obviously not a particularly great sorting algorithm, right? Because I can't even define its bounds, really. If n is really small, you could implement this. You could write this code in Java, Python, whatever. And if you make n relatively small, this will work. Eventually you'll get lucky. But that's not going to last very long. Because as n grows, like look, there are a total of 8 times 10 to the 67 permutations of 52 cards. All right? 8 to the 67. That's 67 zeros. It's a lot of zeros. So you've got a 1 in 8 times 10 to the 67 shot of getting this right. So this probably isn't a very good sorting algorithm, is it? To put this in perspective, because it's, humans are really bad at wrapping their heads around big numbers. We can't do it. We suck. As soon as numbers get big outside of our everyday ideas of what numbers mean and what they represent, we can't wrap our heads around how big that really is. So to put this in perspective, there are roughly 2.4 times 10 to the 67 atoms in the Milky Way. Atoms. Atoms. Okay? I'm not talking I'm talking about particles. Okay? So, if I assigned every single permutation of these cards to each atom in the Milky Way, I'm going to run out of atoms. There won't be enough atoms. I'm going to have 5.7 times 10 to the 67 atoms left over. This sorting algorithm is terrible. It's not going to work at all. If n is small, you'll get lucky. If n is big, this isn't going to work. But of course we know this. This is a stupid sorting algorithm. But at the end of the day, it could work. And what I'm trying to stress here is two big things. Wrap your head around big numbers. It's always important, especially when you're talking about computational complexity, to get a sense of why this could be important. But for a sorting algorithm to be correct, I give it input, and it needs to give me the correct output. Right? That's all it needs. So a terrible algorithm could still be correct. It's just terrible. It's not only about having a correct solution, it's about having a good solution that's correct. And there's a difference. So a lot of people, when they take computer science, they like to play this game of, well, but I was right. I was right. How can you take, it was correct. It's not about just being correct. It's more than that, right? But this has been the spirit of everything in this course, right? The code you write needs to be good, All right, so now a decent sorting algorithm. Let's refresh this page to see if we can get this GIF to start over. Come on, if I click it. All right, well, this is terrible. So here's the idea of bubble sort. You are always comparing adjacent elements. That's the two red boxes. And if those adjacent elements are out of order, you flip them. So look, 6. So it's going to compare 1, 3, they're fine. 3, 5, 5, 2, flip them. 5, 4, flip them. And you start over because, as you can see, doing a single pass isn't going to sort anything. But here, look, it started over. Watch what's going to happen. 6 and 8. Okay, 8, 7. 8's bigger than 2. 8's bigger than 4. After a single pass, one element is where it belongs. The biggest element. Because, and why is this the case? Let's use our intuition. If I'm comparing adjacent elements, and they're out of order, you flip them. Meaning the bigger one moves up. And then you move to compare the next two. The bigger one moves up. Then you compare the next two. The bigger one moves up. It's always going to get to the end such that the biggest one is going to get to the end. It has to. Now, you'll notice that on the next pass, you don't actually need to compare it with the last element, because I know 8 is the biggest element. Flip them, flip them. There's no need to compare 7 and 8, because I know 8's where it belongs. But after 2 passes, the second biggest element is where it belongs. After 3 passes, which element do you think will be where it belongs? The third biggest. After n passes, how many elements will be where they belong? N. Really, you only need like n minus 1 passes, because when the second smallest element is where it belongs, the smallest element must be also where it belongs. But whatever. So this is bubble sort. This is one of the sorting algorithms that you may have used before. But compared to the other two big ones we're going to talk about, this one I think is a little less popular. But this is going to work. Compare adjacent things. If they're out of order, you flip them. You get to the end. After 1 pass, you're not done, but one element is where it belongs. So the general idea, so this is what's interesting about bubble sort too, that a lot of people kind of miss, is if any adjacent number is out of order, you flip them. Now, the order in which I apply these flips doesn't matter. This GIF here scans left to right. All right? It goes left to right because we like to have a systematic way of doing it, but really it doesn't matter. All I have to do is just repeatedly look at that collection, and if there's anything out of order, you flip it. And you just keep doing this. And the order that you do it doesn't matter. All that matters is that you get to the solution. And it will work. So let's say I have 4, 3, 2, 1. Well, I could flip those to, I'm just flipping them in any arbitrary order, but it doesn't really matter. But of course, arbitrarily selecting pairs, whatever, we like to do it more systematically, so we'll start left to right. Pass 1. 4, 3, you flip them. 4, 2, you flip them. 4, 1, you flip them. After 1 pass, there's no way to guarantee that this is a sorted collection. But we can guarantee that the biggest element is where it belongs. It must be. Does anyone have any questions about the intuition as to why the biggest element must be where it belongs? let me put it this way. If there was an element that was bigger than 8, and it wasn't at the last spot, we must have done something wrong, because if it was bigger, it must have been, it would have had to have been flipped to move up. Either 8 was compared to that bigger element, let's say it was a 9 in that example. If 8 was ever compared to 9, they must have been flipped, but they weren't. So 9 must not be there. If 8 was never compared to 9, then we missed something. It should have been compared to 8 and 9 should have been compared at some point during that scan. There can't be a bigger number. Yeah, but the largest value in the list will have bubbled up to its correct spot. The trick is to repeat this process until the list is sorted. So we know 4 is in the right spot, so compare 3, 2, compare 3, 1, done. The next pass, compare 2, 1, well, we do and then they flip. 3, 2, 1, 4. Should probably have the out of order one here. Anyways. I would only need 3 passes for this to be correct, n minus 1 passes. So worst case scenario is the example above. I mean, this depends on the algorithm, the way we implement this algorithm, really. But the worst case scenario is the example above. I get the elements in reverse order. I'm going to have to keep doing all these passes. So the above example, okay, the question, how many passes must be done to guarantee that it's sorted? If the list is length n, and after a single pass, the largest value is in its proper location. After the second pass, the second largest in its proper location. After the third pass, the third largest. How many passes do I need to do in order to guarantee that all n things are in order? N, or n minus 1, because we know that the last one's a freebie. So, after n passes, it's guaranteed to be sorted. Yeah, okay, that's just me saying n minus 1. Okay. The best case scenario is, well, I give you a collection of the things already sorted, right? I just go and I go like, are they out of order? No. Are they out of order? Are they out of order? No. Oh, okay. If I swapped nothing, they must be all in order, right? If nothing needed to be swapped, that means that everything was in order, therefore it's sorted. Yay. So we can look at the algorithm. What does it say? Okay, well, the list is not sorted. For each adjacent pair of values, if they're out of order, swap them. Note that the list is not yet known to be sorted. If I ever swap something, I'll be like, okay, I swapped something, therefore I can't guarantee the list is sorted. That's the algorithm. Really, that last line isn't necessary, because I can guarantee that after n minus 1 passes, I know it'll be sorted. But we could stop the search early with that little flag idea. Basically, imagine I'm applying this algorithm. Okay, as far as I know, this collection is not sorted, right? So for each adjacent pair, if they're out of order, we swap them and take note that the elements are not sorted anymore. So, okay, 1, 2, they're fine, 2, 3, they're fine, 3, 4, they're fine. Oh, so I'm never going to note that they were not sorted, therefore they must be sorted, therefore I'm done. Great. Or I could do this 2 more times to guarantee it's sorted. But if I ever have to do a swap, I can go like, okay, well, on that last pass, I had to swap something. Meaning, I can't guarantee that this is sorted anymore, so I'm going to need to do at least 1 more pass. As soon as I ever do a pass where nothing was swapped, let me rephrase that. When I do a pass where I swap nothing, I can conclude that, okay, they are sorted. So how much time does it take? What's the computational complexity of doing 1 pass? There's a list of n elements. N. I got to compare. It's linear. Realistically, how many adjacent pairs are there in a list, in a collection of n things? Who can tell me? I'll sit down and wait till someone answers this, because this is embarrassing.
N divided by 2.
N divided by 2? No. You try, though.
N minus 1.
Why?
Because it's like there's.
It's kind of hard to explain, isn't it? Because it is. If I've got n elements, you compare n, or 0 and 1. Then you compare 1 and 2. It's just n minus 1. But of course, that's still linear, right? So to do one pass, it's linear time. And remember, when we're talking about computational complexity, it's not like the absolute work. It's how much does the work scale relative to the input size. If I double the input size, the amount of work I need to do doubles. So to do one pass, it's linear time. And how many passes do I need to do to guarantee it's sorted in the worst case scenario? We talked about this like twice already. I'm going to be honest. If you don't want to be lectured at, I don't want to lecture at you. We can wrap it up now if you want.
N minus 1.
N minus 1. So if I have to do, so like linear a number of times. If I double the size, I have to do more passes. I have to do twice as many passes. So if I have to do linear work n times, the worst case scenario is the computational complexity is n squared. I have to do n units of work n times. Now the best case scenario is it's possible that you give me a collection of things that's already sorted. And if it is, all I ever have to do is scan that collection once, and that's linear time. So best case scenario, it's linear. Worst case scenario is it's quadratic, it's squared. That's bubble sort. Do you think, raise your hand if you think you've ever actually used this before in your life. Yeah, one person, two people. A lot of people will end up using some sort of mishmash of all the sorts that we're going to talk about today. So insertion sort and selection sort, I would say, so first of all, they're kind of like two sides of the same coin. If, when I'm explaining these next two sorting algorithms, you're thinking like, I feel like they're kind of similar. You're right, they are. I mean, there's the differences, don't get me wrong, but they're very similar. And I would say that these two sorting algorithms are actually far more intuitive, and chances are they are ones that you've already, you have used. If I gave you a pile of papers and told you to sort them by alphabetically, you would do one of these two probably. It's intuitive. So, here's the idea. You go through and you find a number. And then you scan. Let me put it this way. This is the idea. The actual algorithmic implementation of this idea is not important right now. The idea is, imagine I have two piles. I have an unsorted pile and a sorted pile. So here's what I'm going to do. I'm going to take one thing out of here arbitrarily, and I'm going to add it. I'm going to insert it into the sorted pile where it belongs. The first time I do that and it's empty, well, that's easy. I just take one and put it in there, boom, done. Right? Because a collection of size 1 is sorted. All right, I do it again. I take out the next thing. Now I need to go, no, okay, does this thing go before or after that one element in there? Put it in accordingly. Then I take another one. Now I need to know, does it go before, in between, or after? Put it where it belongs. and I just build this process up until that is empty. If every time I inserted something into the sorted collection such that it remains sorted, once I'm done emptying the unsorted pile, this collection must be sorted entirely. That's insertion sort. So look, I start with 6, whatever. Okay, I pick 3, where does it go? Oh, it goes there. I pick up 1, where does it go? Well, it goes there. I pick up 8, where does it go? Well, it goes there. 7, goes there. 2, I scan the sorted part and put it there. Now I look up for 4, scan the inserted part, put it there, it's done. Now this was kind of like done. Imagine that's an array, for example. Instead of having 2 separate piles, you could just be like, okay, this chunk of the array is sorted and that chunk of the array is unsorted. Whatever. It's the same idea though. We have the unsorted chunk and the sorted chunk. Every time it's picking something from the unsorted chunk and inserting it into the sorted chunk where it belongs. That's the algorithm. If I have n things over here, this is going to sound like a dumb question, but it's important to answer these questions. If I have n things over here, how many times can I pull something out of it before I run out? N, of course. So for each time I pull something out, I need to insert it into the sorted collection. Now this is a little tricky to think about, but it's not too bad, and we've actually seen this pattern several times before in the course. Let's think about this here. So this is 1. I'll start at 1 instead of 0 and n. Okay? Right? There. I take out the first element. How much work is it for me to insert it into the empty sorted collection? It's constant time, right? I just throw it in the front, whatever. I have to do like 1 unit of work. I take it out and go like, oh, where does it go? Oh, just the beginning. Because it's empty, now there's one thing and it's still sorted, great. So I have to do 1 unit of work. I take out the next thing. Well, now I actually need to compare it to something. I take out the next thing. Now I need to compare it to something. Every time I remove something from here and go to add it there, this list gets smaller, but this list gets bigger. Meaning, every time I add something, the amount of work I need to do to find where it belongs in the sorted collection grows. Right? Because it's getting bigger. And eventually, once I get down here, it's going to be like n. Right? We've seen this pattern before. The first time, it's constant time. The last time, it's clearly linear. I take that last element out. I've got to compare it to everything there. It's going to be linear, obviously. So, how much work is it, on average, when looking at this, how much work is it, on average, for me to find where this element needs to be inserted? N divided by 2. Right? Because for every time it's 1, it's n. For every time it's 2, it's n minus 1. On average, if you added all of this up and divided it by n, you'd end up with n over 2. So, 1/2 times n, that's just a coefficient. We don't care about coefficients. So, what's the computational complexity of that actual scan? Who can tell me? It's linear. Yeah, it's n. It doesn't matter that it's n over 2, it's just a coefficient. It still grows linearly. If I double it, it doubles the amount of work. So if I have to do linear amount of work for each of the n things I'm taking out, how much work am I doing in total?
N squared.
Yeah, n squared. Just like bubble sort, it's n squared. And when you visualize it, you can see this is should be a square, right? But I only have like half the square, right? But we don't care about halves, so it's squared. This also follows that pattern I showed you before. 1 unit of work plus 2 plus 3 plus n minus 1 plus n, right? Remember when we did that? The summing of all that, that's what we did here. That's that n times n plus 1 divided by 2. Which when you look at that, look, if you just take that expression, n plus 1 divided by 2, I realize the marker's fading away. Can you see at the back at least a little bit? Cool. All right? If you look at that, well, you go like, well, okay, that's n squared plus n, 1/2 n squared plus n. We don't care about coefficients. We don't care about the linear bit. We only care about the bad bit. That's n squared. Yeah.
You said you wanted to leave at 55?
Perfect. Thanks for the reminder. Perfect. Thank you. We'll finish. I think we can finish up this bit. So, there we go. We just talked about computation complexity. So, worst case scenario, like we talked bubble sort. The best case scenario is, depending on the implementation, is if you get the elements in order. So is there something similar for insertion sort? Well, it really depends on how you implement it. Because if we go back and look at this implementation starts scanning the list in reverse, right? If you're scanning the list in reverse, the sorted list in reverse, the best case scenario is going to be if the elements are already sorted. Because I add 1, great. Then the next number I get is the next biggest. Okay, it goes right after immediately. Great, I don't need to keep looking. I just keep tacking it onto the end, basically. So the worst case scenario here would be if they're in reverse order. However, this is arbitrary in like the direction in which I started scanning the sorted list was arbitrary. The fact that this starts going in reverse, like it's looking in reverse order to find where it belongs, entirely arbitrary. There's nothing saying I shouldn't have started at index 0. There is an implementation, perhaps there's a coding advantage to looking in reverse order, but that's irrelevant to the algorithm. So if I started scanning the other way, it could have an impact. Although, how much of an impact would it have? If I started with 1, and I add it, and then I add 2, well, 2's got to go on the other side of 1. And then I go to add 3, well, that's got to go on I got to look at 1 and then 2 and then 3 to put the 3 where it belongs. And then 4, I got to look at 1, 2, 3, and then add the 4. So if it was in order, where we started scanning at the beginning, worst case scenario would actually be if you got the elements in order. So the best and worst case scenario here actually depends on the implementation details. But be aware that there is a best and worst case scenario. That's important. For each element in the unsorted list, scan the sorted list to find where the new element goes, insert the new element into the sorted list. Done. Selection sort, I'll just say what it is. Scan a list and find the smallest element. Append it to the sorted list. Scan the list and find the smallest remaining element. Append it to the sorted list. Scan the list and find the next smallest remaining element. Append it to the sorted list. You can kind of see how this is very related to insertion sort. Insertion sort took an arbitrary element and scanned the list to find where it belongs. Selection sort goes through this unsorted and selects the smallest, and then we don't need to find where it belongs, we know exactly where it goes. So it's kind of like a flip, but we'll talk about this on Tuesday.